But if that's the case, then that definitely gives me more reason to do this one than that one. If nobody's gonna be here after 5, I might as well not be here after 5. But I was thinking, because I'm gonna be here till 3:30 in meetings with other people, but I have to move my office hours anyway. That would be a way to do it. But if you guys are in agreement that that's less ideal and we're better off switching to doing that on video, that means that probably sometime during this week, I will simply record the thing and post it Friday morning like I was posting it after class. I don't have a problem with that. But does that seem to be more what people want? That to have the review day on Monday when we get back, rather than Friday before review? All right. Then we'll go with this one. And I will email you all a new version of this and post it, rearrange the dates appropriately. But meanwhile, all right. So this is the new. Wrong button. There. That's very reasonable. Okay. When we talked about the chain rule, we talked about the first version, we talked about the derivative going along a path, right? So I had this path, x of t, y of t, and I measured the change along that path as t increased. I want to take this idea a step further. I want to be able to take a derivative in any direction at all. And when we think about partial of f with respect to x, I can think of this as the derivative in the direction I. Because really, it's change in f as we move forward in x, and the vector that points forward in x is I. And then I can say the same way, partial of f with respect to y in the j direction. I want to go another way. So the I direction points forward, the j direction points to my left, v points in an arbitrary direction. What's the change going that way? All right, wait a minute. I gotta go back to my image, otherwise it doesn't make a damn bit of sense. Partial with respect to x went forward. Partial with respect to y went to the left. Partial with respect to x went forward. Partial with respect to y went to the left. Now I'm going in a different direction. So what if I want to go this way? Or that way? Or that way? I need a new vector. gonna go that way. Well, I can think of that as a combination of going forward and left, right? Correct? Well, wait a minute, page 947, figure 3. I can think of this direction in the direction V, AB, as going some bit forward in X and some bit in Y, and then linear approximation, combining those two changes. First go forward, then go left. First go left, then go forward. I make a little triangle, and that triangle is visible down here in the XY plane here. So I can think of going in this direction and making a new curve and cutting a tangent line there. This really only works best if I turn this vector into a unit vector. So instead of using an arbitrary vector, I'm going to use a unit vector. That takes any versions of the length of u out of the game. Sorry, the length of v out of the game. I don't care how far we're going, I just care what direction we're going. Then I'll do my derivative calculation. That's h times u1 with the x0 there. This unit vector u will be u1, u2. So really what I'm doing is I'm saying, oh, well, let's do the exchange. How much I ever went forward from that vector. And let's do the y change, however much I went sideways from that vector. These ratios are from here. But that's literally a linear combination. That's just the sum take the x derivative, multiply by how much you went forward. Take the y derivative, multiply by how much you went sideways. You're literally just averaging the two proportionally. It's a weighted average. How much weight? How much did we go forward? How much did we go sideways? Notice, if we're going in the I direction, then A is 1 and B is 0, and we just get partial derivative with respect to x. If we're going in the y direction, that's J. A is 0, B is 1. We just get partial with respect to y. It's an average between the two. I'm going to call this the directional derivative of f at x0, y0 in the direction u. Because that's what u is. U is a direction. It's a unit vector, just tells me which way I'm going. The symbol for this is d sub u of f at the point x0, y0. You don't always have to put the of f in parentheses. Sometimes you'll see that without this set of parentheses. Du f of x0, y0. So now I have a new symbol for derivatives. D sub u, where u tells me the direction. An example. F of xy equals x cubed minus 3xy plus 4y squared at the point 1, 2 in the direction theta equals 30 degrees or pi over 6 radians. Now, that's a vector in standard position, which means that is with respect to the x-axis. So that 30 degrees is measured from x in the counterclockwise direction. Which means we're going that way. North of east. I know how much this function is going to change if I walk true east. I know how much this function is going to change if I walk true north. But now I'm walking east of north of east. Which way am I going? Up or down? I need my partial derivatives. The directional derivative is the partial with respect to x evaluated at the point 1, 2. Oop, can't see squat. It's down here. Times a plus partial derivative with respect to y evaluated at the point 1, 2 times b. Oh, wait a minute. I need the unit vector ab. What unit vector do I have? Right. But that would be the vector here, right? But I'm looking for the vector at this angle. So I am actually at the point 1, 2, going in a direction this way. So the unit vector is up here. It's not going to 1, 2. It's going from 1, 2 in a given direction. So what is this unit vector? Say that again. Got to do the trig numbers correctly. I need cosine and sine, right? So cosine of 30 degrees and sine of 30 degrees are root 3 on 2 and 1 on 2. You were doing, well, if you're over root 2, then you're doing 45 degrees. The unit of 1, 2. Well, that would be over root 5. But that's I don't want to use that one at all. That would be a unit vector this way. I wouldn't even get to the point, right? The point's further away. But now I have u, so I need my partial derivatives. There's the function at the top. What's partial of f with respect to x? And partial of f with respect to y? I can do partial derivatives. Partial derivatives aren't that insane. The derivative of x cubed minus 3xy plus 4y squared with respect to X. Yes. And then I evaluate that at 1, 2. I get three minus 6, -3. Partial of f with respect to y. And again, at the point 1, 2, so my directional derivative is -3 times root 3 over 2 plus 13 times 1/2. Okay, before I go any further, let me ask you one question. I'm standing here, I'm walking in this direction. Am I going uphill or downhill? I'm standing at this point. I'm going in this direction on this surface. Am I going uphill or downhill? Why?
Y is like the direction that you go in the Y axis.
But I'm going in partial X and I'm going in partial Y, and I'm going more in X than I am in Y. But according to this, I'm going up more than I'm going down. This number is positive. Three times the square root of 3. Square root of 3 is less than 2. That number is less than 6. This top is 13 minus. That's a positive number on top. Positive over positive. This is positive. As I walk in this direction, I'm going uphill. For every 1 foot forward I go that many feet up. Because this is a positive number. What if I changed direction? What if I, instead of going 30 degrees, I went at 135 degrees? What would change in this entire calculation? My unit vector would change. But these two numbers wouldn't, right? Because I'm starting from the same point. Only these numbers would change. So those would be the same. No matter what direction I pick, the only part that's going to change are going to be these numbers. As long as I'm at this point. Questions? If it works for 2 variables, it works for more. Now I'm going to say I'm very happy that I cheated. I'm giving you a unit vector to start with. So I am at the point 302, 302, and I'm going in the direction positive 2/3. That should be negative 2/3. It's really hard to read like that. Negative 2/3. So I'm going in the positive X, negative Y, positive Z. So I'm going this way. How do I measure change? I do exactly the same thing. I need partial with respect to X at the point. I need partial with respect to Y at the point. And I need partial with respect to Z at the point. So I'm going to have to do 3 partial derivatives. So what's the derivative of this thing with respect to X? So that's e to the 2yz evaluated at my point. So that's e to the 2 times 0 times 2. That's e to the 0. That's 1. Derivative with respect to y. Because I got to use the chain rule, right? Derivative of e to the stuff is e to the stuff times the derivative of the stuff. So that's x times 2 times z. That's 3 times 2 times 2. That's 12. E to the 0 again. So that's 12. And then with respect to z, x stays in front. E to the stuff, chain rule gives me 2y. E to the 2yz. So I get x times 2 times y, that's 0. It's 0 e to the 0, but the 0 wins. And then I have my direction vector. So to actually compute my directional derivative, what do I do? du of f at the point 302 is
Right. 12 times negative 12 through. Let's see.
I'll write it as 0 times 1 on 3 so we can remember that we multiplied each one of those partial derivatives with each one of the pieces of my unit vector. Now again, 2/3 minus 8 plus 0 is negative 22 over 3. This is a negative problem. This doesn't mean the same thing about going uphill or downhill because it's a fourth variable, right? The value of f is changing when I go from here in this direction. The value is changing negative. Maybe this is temperature. Temperature is going down when I go this way. Maybe this is the concentration of a certain chemical in the air. It goes down when I go in this direction. I don't know what this fourth dimensional function means, but I can interpret it in lots of different ways. But it means that the change is negative. When you go from here that way, whatever you're measuring is decreasing. You're looking at me like you hate this explanation, Ben.
I would just say about
There's no visual graph for it. What I see in my head is chemicals in the air. So I see this like gas and it's getting lighter in color as I go this direction, right? Or I think of temperature being like from red being hot and blue being cold, we're going from redder to bluer. But I'm moving in 3 dimensions, and we don't often do these graphs in 3 dimensions. We always do these graphs flat. So it makes more visual sense in 2 dimensions, but the idea can be expanded. More questions? I've seen that thing before. Number times number plus number times number plus number times number. The hell is that boxed expression? Think vectors. We have a unit vector here. Where does something like this come from when I'm doing vectors? I'm having the weirdest sense of deja vu, man. And not only is it a dot product, the second part of it is u. This was the vector u. So what the hell is this? Well, that vector came from my partial derivatives. I'm going to write it like this. Partial with respect to x at the point P. Partial with respect to y at the point P. Wait a minute, I'm going to keep writing that at P inside. Let's write it outside. You take the partial derivatives and you evaluate them at the point. I like writing the outside at P. That makes then this whole thing, that makes this a vector I get from F. And it measures change in all the directions we can go. Our previous version, the one we did where we're talking about going uphill or downhill, we had Fx and Fy. And then we evaluated that at the point 1, 2, right? The one we just did here, Fx, Fy, Fz, and we evaluated at the point 3, 0, 2. And that's how we got this vector. I like this vector a whole hell of a lot. I am going to call this vector the gradient of F. Now, the gradient vector has as many entries as we have independent variables. So if my function is a function of x and y, the gradient looks like this. If it's a function of x, y, and z, it looks like this. If it's got 5 variables in it, it'll be a 5-dimensional vector. That's fine. I don't care how many letters it's got. The symbol for gradient is an upside down capital delta. Technically, that upside down capital delta is called a nabla. Barely anyone uses that phrase. I called it gradient all the damn time. One of my students called it nacho because it looks like a chip. I'm fine with that. Nacho F works for me. But that means I can give you any function you want. That's the function we were just doing, right? The gradient itself doesn't actually plug in the points. The gradient is a function. If I give you the function f of xy equals square root of x squared plus y squared, what is the gradient of that function?
Through square root of x squared plus y squared. Wow.
Almost. You made a chain rule error.
Is it no two?
Correct. Because you get a 1/2 stuff to the negative 1/2, and then the chain rule gives me the 2. So there should be a 2 on top here and a 2 on top here, or there should be no 2's on the bottom. Make sense? Okay. Here's the best part. Yana, you said this was a dot product. But it's the dot product of the gradient at the point with my direction vector. So the directional derivative where P is some point is found by first taking the gradient, plugging in the point, and then taking the dot product with our unit vector. That is a much shorter formula to remember than having to figure out extra, but it contains all the same information. Take the x derivative, take the y derivative, take how much you go in each direction. Well, that's the dot product. Question. Reach a little back further in your memory banks. What's another way to figure out a dot product? There was another formula we had for a dot product. Chapter 12, section 3. A long time ago when a galaxy far, far away. Length of A, length of B, right? Well, if I do that same thing here, that would be the length of the gradient times the length of our vector times the cosine of the angle. Wait a second. What do I know about the vector u? The length of it is 1. It's a unit vector. So, 2 questions now. What is the biggest possible value I can have here for cosine theta? 1. When do I get a cosine equal to 1? So if the unit vector and the gradient point in the same direction, the directional derivative will be as big as possible. But wait, if that's as big as it can possibly be, then cosine of theta is 1, and the size of this is the length of the gradient. Which means the gradient tells me two other pieces of information automatically. The gradient tells me which way to go uphill the fastest. And it tells me how fast I'm going up by taking the length of the vector. Wait a second. I got to go back to that first example again. The first example had x cubed minus 3xy plus 4y squared, and we were at the point 1, 2, right? So let's work out the gradient of f at this point. We worked out the partial derivative. Partial derivative with respect to x was and the partial derivative with respect to y.
-3x, say what?
And now if we evaluate that at the point 1, 2, that's how we got -3, 13, right? Which were the numbers we multiplied by the vector. But now I can say, wait a minute. The direction that goes uphill the fastest is that direction. If I'm standing at the point 1, 2, and I want to go uphill the fastest, I should be going back that way. Right? Negative x, positive y. I should be going back that way. That'll go up the fastest. And our slope going in that direction is the length of that vector. But wait a minute, I know what the length of that is. Square root of 9 plus, what's 13 squared? 169. So that's the square root of 178. Which is bigger than like 13 point something, 13.2-ish. No, 13.1 something. Regardless, that's the direction I go back and up. I'm going up pretty damn quick. Wait a minute. If that's the direction I go up fastest, what's the direction I go down fastest? When is this as small as it can be? No, that's when it's as big as it can be. The angle is 0, it's as big as it can be. Cosine of theta will be 1. What's the smallest you can get for cosine of theta? -1 at 180 degrees. Well, wait a minute. 180 degrees away from this is the opposite side of the same line, isn't it? So I know the direction we go down fastest as well as up fastest. If going in this direction is the fastest up, then going exactly the opposite way is the fastest down. Okay. You've seen this in real life. I want you to imagine you are standing outside of a lot. Out by the clock. Outside of Haiti. And it's raining. What do you see in front of you on the street as it's raining? Water. Water moving, I hope. Which way? The fastest way down. At every point on the side of the hill going down to B lot, going down A lot from the backside where the dorms are towards admin. We're going slightly downhill. The water's going that direction. At every single point, we move in the direction of our gradient. This is a hillside. Notice the contour plot shows me the heights at all these different points. I stand at some point and I find the gradient. If I let down a drop of water right there, it goes in that direction. Well, 180 degrees from it to go down as fast as possible. That curve is perpendicular to the contours of the contour plot at every point. Because here on the contour, your change is 0. Those are all at the same height. So the fastest change is at a right angle to that. The fastest path up must be perpendicular to those level curves. The fastest path down must be perpendicular to those level curves. And this is why weather maps work. Because a weather map gives me the pressure in bars at all these different points. There's a low pressure here and a high pressure here. There's the difference from Kearney, Nebraska to Sioux City, Iowa. K&S. Those are the two cities right there. Low pressure here, high pressure here. Which way does the wind blow? Wind blows from high pressure to low pressure, right? High pressure is pushing away, low pressure is the air's going in. So what path does the wind take? Path takes. So the wind takes a path determined by the gradient at any given point. And those gradient vectors must be perpendicular to those curves. The wind goes this way. In towards the area of low pressure. Now, because the Earth is turning, the wind vectors kind of rotate a little. So you don't get something that just goes straight in, you get a twist like a storm system, right? There's a front. The front moves in the direction perpendicular to those level curves. At every single point on this set of curves, I could draw the gradient vectors. There. This is now a contour map of a hyperbolic paraboloid. Remember our hyperbolic paraboloid? The curves go down in one direction and up the other direction. So these curves are low. See, the heights are negative. These curves are high. The heights are positive. So this is going up to the left and right and down up in the y direction. So the fastest way down is this way. The fastest way up is this way. Those curves follow the gradient vectors. I could draw paths along those blue vectors, couldn't I? Those paths would be perpendicular to the red curves everywhere they cross. Didn't we talk about orthogonal trajectories when we did differential equations last semester? This is where they are. Let me change the picture. Suppose this was temperature. Then this is the direction that the temperature heats up the fastest. This is the direction the temperature cools down the fastest, right? It is 30 degrees this morning when I get out of bed. My dishwasher ran overnight. I open the dishwasher, take out a glass, what happens? If my dishwasher just finished, that glass is pretty hot, isn't it? I take the glass out. The air is really cold. Why? It cooled too fast. Thermal shock set in and the glass shattered. I wish I was making this crap up. I broke a wine glass at my parents' house because of this. I opened a brand just finished washing machine. I opened it, opened the drawer, and I started to hear the clinks. And a bunch of the glasses in the top rack shattered. This is why if you open a washing machine, a dishwasher today, right after it finishes, it yells at you. Bing, 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 bing. We haven't cooled down yet. Don't open the damn door. Take that same idea of thermal shock. If I have a function that describes temperature in 3 dimensions, which way do I go to cool off the fastest? I follow the gradient. Well, 180 degrees from it, right? I'll get warmest this way, I'll get coolest this way. But if I go too quickly, things will cool off too fast and things will change. So I have to figure out what direction to go to cool off at the right rate. Useless stuff. I'm never going to see it anywhere. I prevent hulls from popping this way when I dive in a submarine. If I take too steep of an angle, the temperature change is too severe. And the hull contraction happens. That's not a good thing. But the fact that these are perpendicular tells me something better. Let's suppose I had a function of 3 variables again. The set of points where that is equal to some number, that's a level surface. If I take the gradient at some point on this level surface, remember, this is a level surface. If I go along the surface, there will be no change. And that means the gradient will be perpendicular. Wait a minute, my gradient is perpendicular to the surface. It sticks out of the surface at 90 degrees. Look at my hand. Isn't that a tangent plane? My gradient is the normal vector for my tangent plane. I believe it's page 955, example 8 walks you through one of these. The gradient gives me a whole crap ton of information that shortcuts some of the processes that we were doing earlier. To find the normal vector, I had to find all of these partial derivatives. But wait a minute, I can get that right from the gradient. That's a faster way to do this. The picture of the field. We're going to do more of this, but it's going to take a little while longer. Vector fields are an important piece. But that's not until Monday. So it seems to be that the overall desire is to do this version, since you all have to get out of the dorms quickly. Having late office hours is a bad idea. I will send out a video. We will cancel class, send this to you in an email as well. And I'll post this as the new version on our Canvas page, but that'll happen over the weekend. Thank you all very much. I will see you all on Monday.
Have a good day.
Right.